Hello, good afternoon, everyone. Welcome to the session 2 of our course on large language model. Today, we are going to explore a very exciting frontier in AI, and it's about how we can bridge visions and language using the multi-agented AI systems. My name is Junke Xu, and I will be guiding you through today's lecture and the lab. If you want to build your own applications by using the computer vision, large language models, and intelligent AI agents, you will have some deep dive into some of the most cutting-edge research and applications out of here. Yeah, let's get started. Yeah. Let's begin with a practical problem, activity pole inspection, which will be our lab today. As we all know, activity poles are everywhere in our daily life. It's crucial for some port delivery and telecom infrastructure, but they are also exposed to the element and some physical wears and also some unexpected damages on that. Traditionally, inspections are carried out manually. That means people on the ground checking the posts one by one, often in remote or hazardous locations. It's expensive, time intensive, and subject to some inconsistency. What we have been exploring is how to automate this process, not just detect whether a pole is damaged, but also generating a meaningful report that could be used by engineers or maintenance crew directly. The idea is simple. Take an image of the pole and let the system do the rest, understanding what is in the image, access the conditions, and return the structure. Human readable summary. And this is not just about some saving times, it's about improving the accuracy, repeatability, and safety of some infrastructure monitoring. And these use cases also give us some perfect lens to explore some of the key technology we will be covering today. So from computer vision to language models and how they work together in more advanced multi-agent systems. Here is how we are going to structure today's session. We'll begin with all the knowledge stacks of our applications. First, we will take a look at the multimodal large language models, what they are, why they are matters, and how they go beyond traditional large language models. Then we will introduce key reasoning techniques called chain of thought, which help model break problem down step by step, especially useful when we ask them to explain or justify their output. Next, we will shift into the computer vision, where we look at how models interpret visual data and how we can combine them into the language understanding. Once we have these fundamentals in place, we will talk about AI agents. Module components that carry out some specific task in the large system. This ties directly into the demo we will see later. And we will then revisit some lab agent structure of our demo. And this time we will focusing on some technical perspective breakdown into some component of the solution. After that, we will walk through some coding tutorial today to see the system in action, and you will get a hands-on view of how the pipeline works from input to output. And towards the end, we will have some quick quiz like previous we have, and to review the key concept, and we will have the QA part and the final. Okay, and let's begin with multimodal large language models. When we talk about it, we are thinking AI systems that can work with more than just text. For example, traditional large language models only process language they can read, generate, and reason over words, but they cannot see any images, interpret a video, or understanding audio signals. But multimodal large language models change that. So they are built to handle multiple types of inputs, like text, images, audio, and video, and process them together into a unified way. that open the door to much more natural human-like interaction with AI. Let's work through how it works, just like what you have seen in this picture. On the left side, we will start with some input from different modalities. First is text and images and audio and the video. Each type of the input goes through its own encoder. For example, an image encoder for some visual content or an audio encoder for some sounds. Yeah, after encoding, each input passes through an input projection layer. This step translates each modality into a format the core large language model can understand. Once everything is projected, all the modalities are aligned and fusing at the center where the large language model operates. And at this point, the model has shared the understanding of all the input. It can, for instance, matching a phrase in the text to a visual feature into an image, or understanding how speed corresponding to the video it comes from. Now, on the right side of the picture, we can see output generation. Once the large language model has reasoned over the multimodal input, it sends its output back through the output projection layer and then into some diffusion model, which generates final output into the original form. That means the model can generate an image based on the text prompt, and it can produce speech from some writing content or even create video by combining multiple inputs. So what does this enable? Imagine a healthcare application where a model reads some medical notes and exam an X-ray, and at the same time, it can offer a diagnosis based on the both two, or for some business setting, when the model reads the PDF with some text and a chart and extract insight that combine both. Of course, building multimodal large language model isn't easy. It requires some high computational power, complex training with some cross-modal data, and also some smart design to handle this different input efficiently. But the result is worth it. AI that can see, can hear, and understand the world like what we do. So now that we have seen the what is a multimodal large language model, and let's compare them directly to traditional large language model across several key areas. First is like data pre-processing. Large language model work only with the text. They're using some tokenizer to break down some language data into place the model can understand. And for multimodal large language model in construct are built for multimodal data. It's not just for the text, but like images, audio, and more. This means they need a different encoder for each type of the input. Next, we will discuss about the module architecture. Large language model use some single stream transformer architecture optimized for handling non-sequence of text, but for multimodal large language models using some separate encoder for each input type. These are following by some fusion model that bring everything together into one shared representation. When it comes to the training objectives, large language models are trained to predict the next word. That's what makes them fluent in language. For multimodal large language model, often using the constructive learning, the goal of them is to align different type of data, like matching a sentence with the right image. And inference and capture complexity for large language model already have some high computational cost due to the self-attention mechanism, which deals with the length of the text. But for multimodal large language model are even more demanding. They add some overhead of encoding and decoding multiple modalities at once. So for the modality encoders, large language model only need to handle the text, so no extra encoder are needed. But for multimodal large language model, they have images, audios input into embeddings, so they need this encoder to numerically represent and to capture the meaning. And then it's like an input projector. Large language model process text directly, there is no need to align it with any other input. But for multimodal large language model, align different type of the data, combine them into the single input or model can reason over. For the large language model backbone, for large language models, the backbone is built for the text understanding, but for the multimodal large language model, the backbone process for fusing data allow it to reasoning, generate content, and understand across the format. For the output projection, large language model don't need to convert the result back to other format. Their output is just the text. But for multimodal large language model, often need to convert their internal representations back to images, audios, or other format, depends on the tasks. Finally, modality generators. Large language model don't generate anything beyond text. But multimodal large language model can produce output in different formats, like generating an image from a caption, often using some techniques like diffusion models. Yeah. So overall, while large language models are powerful in language tasks, multimodal large language models are built for the richer, more human-like understanding of the world. But with that come add complexity in design, training, and deployment. Okay, let's look at a more everyday example of where multimodal large language model already provide some useful use cases. The first is digesting note-taking. This is somewhere many of us do all the time. Like, for example, whiteboard session, handwriting notes, lecture slides. We capture them using photos or tablets, but turning this visual into some structure searchable text has always been the challenge. With multimodal large language model, we can bridge the gap. These models can process an image of a handwriting note or a whiteboard diagram, interpret them layout and the content, and also generation some cleaning organization summary in natural language. That includes not just reading the text, but understanding the context. For example, turning bullet point into some full sentence, reformatting list, or some translating between languages. So in academic city, this can mean auto-generating lecture summary for Slack days, or transcribe diagrams alongside explanations. In business, it might mean capture some snapshot of the brainstorming session and turning it into some action items or some meeting minutes. What makes multimodal large language model essentially suitable for this? It's the ability to combine OCR, optical character recognition, with semantic understanding. This don't just extract text. They understand how that text is structured, what it is related to, and how to represent it clearly. This kind of functional brings AI closer to being a real productivity partners, helping us move from unstructured visuals to usable knowledge with some minimal efforts. So let's jump to the next use cases. One practical application of multimodal large language model is in the construction about is safety compliance. For example, checking whether workers are wearing hard hat on site. In this case, tested the scenario by giving these three leading models like GPT-4o, Lava, and Apple's Ferret. We will to doing this, we will upload an image along with some prompt asking them to count and located all the hard hats. Now, it's important to note that these models don't draw some bounding box themselves. They typically return the coordinates value or textual description of the locations. It's up to some, if you have some downstream system, it can have some visualization tools or UI to return this into some bounding box. So with that in mind, we can see from here, GPT-4o have the rich screen description, but some of the coordinates it returned were really invalid. It's falling to outside the image boundaries. So only one usable detection appears in the picture. For the lava, missed one of the hard hat entirely, and especially some one particularly hidden, and it also returns some coordinates, but they weren't really accurate. But for the Apple's favorite did the best. It correctly identified all the four hard hat, including the hidden and on the left, and provide some coordinate for that. But this comparison highlights some practical challenge of using multimodal large language model for real-world visual tasks. Detection is one part, but the accuracy, completeness, and interpretability of the output matter just as much, especially in the environment like construction, where the safety components isn't optional. Model need to be reliable, not just in what they are described, but in how accurate they localize the objects. Another high impact use cases for multimodal large language model is autonomous driving, where model need to interpret complex visual screens in real time and make decisions based on them. For this example, it used a frame from some actual driving dataset. The prompt we gave the model was more challenging, not only to detect vehicles and pedestrians, but to evaluate some potential risk from some perspective of the self-driving cars. The results were telling here. For GPT-4o, it delivers some detailed and well-reasoning textual response. It's identified some general risks, explained some possible outcomes, and even mentioned some safe navigation strategies. But once again, when it comes to some accurately localization some objectives, it feels really short. The bounding box coordinate were off, make it unusable in some perspection pipeline. For the lava, the open source model struggling here. It completely misses the large track directly in front of the car, which is argued the most critical objective in the screen. This kind of hallucination raises real concern about the reliability in some safety critical applications. Apple's favorite was also standing out here. It detects the majority of some objects, include both vehicles and pedestrians, and return some valid boundary box coordinates. It was the only model that could tie recognition to localization accurate in the scenario. These use cases show how important accuracy and the reason are, and how few models do both well. For autonomous system, it's not enough to describe the screen. You need to have some accurate detection, reliable spatial awareness, and the ability to reason about some risk and intent, all under time and constraints. We are getting closer, and the results show even some top-tier model like GPT-4o have some significant gap depending on this task. That part's what driving ongoing research in combination vision and language more effectively. So far, we have talked about how multimodal large language model can perceive complex multimodal input like image, text, and chart or video, and unify them into a shared understanding. But the perception alone isn't enough. In many real-world tasks, the model also needs to some reason through what it sees, often step by step. So that was where chain of thought or COT comes in. COT is prompting and reasoning techniques that can encourage model to behave more like a human, do when solving problem by breaking tasks into some smaller sequential steps instead of jumping strategy to the answer. The concept is simple. Instead of asking the model for a final answer, we prompt to think out loud, mapping out the intermediate steps, doing calculation, identifying relationships, or walking through a decision-making process. This is especially useful in the tasks that require some multi-step reasoning, like in complex math, logical puzzles, visual analysis, or some real-time decision making. Without COT, even some large models often fall short, and they are training to predict the next word, not necessarily to solve structured problems. COT help guide the model's behavior by encouraging methodical, logical thinking. A typical COT prompt does a few things. It encourages step-by-step processing rather than rushing to the conclusion. It generates some intermediate steps. For example, identify some key piece of the information, performing a basic operation, then using the result in the next step. And it maintains some coherence across steps, make sure each part builds logically on the previous one. COT can be learned through some few short prompting, or more robustly through some fine-tuning multi-step reasoning dataset. When combining with multimodal large language models, COT enable not just understanding what's in an image or document, but also reasoning about it, explaining what is important and making information judgment across modalities. So what does the COT actually improve, and why are we use it in the modern AI system? First and foremost, accuracy. By breaking down the complex task into some smaller steps, COT help model avoid the kind of errors that often come from one short answer. In math, for example, it allows model to solve for variables individually, verify internim steps, and reduce some compounding mistakes. This structured reasoning doesn't just improve the outcome, it also makes the process more interpretable. With COT, you are not just getting an answer, you are seeing how the model arrived at that answer. That kind of transparency is critical in domains like in healthcare, law, and in finance, where it's not enough to be right. You need to be able to explain and trust the process. For instance, in the medical diagnosis, a COT-enabled model might suggest possible conditions, but it will also walk through some symptoms, test result, and some logic behind that suggestion. That gives some professional a way to validate or challenge the AI reasoning. And finally, COT help to generalization models trained or prompt with COT technique to perform better across different type of tasks, not just for language or logic, but also for math, science, even multimodal input. Because the model is reasoning step by step, it's better able to adopt its logic to unfamiliar with problem. And that makes it far more useful across industries, especially in domains where structured thinking is essential. Here is a concrete example of how COT reasoning can reshape the learning experience. What you see in this picture is a COT AI tutor guide a student through the math problem step by step. Note that the AI doesn't just giving an answer. It first identifies the key part of the problem, then understanding the logic behind each operation, and only then arrive at the final solution. This is the essence of the COT in education: structured, transparent, adaptive reasoning, and it can support actual understanding, not just memorization. Now, imagine this scale up. The AI tutor adjusts explanation to fit the student learning pace, offers multiple ways to solve a problem, and allows student to ask why at any step. This interaction can resolve the way education is delivered. Students who struggle in traditional setting can receive some personalized instruction anytime, anywhere, and at a level that fits their need. This will not only improve outcomes, but also democratize across the quality education, especially for the learners who don't have some consistent access to the quality teacher or some resources. So with COT, AI is not longer a tool, but become an assistant in some learning process. It's able to interpret, adapt, and even encourage deeper thinking. Here is a first example of how COT reasoning can transform professional workflows. In this case, is a legal service. On the left, you see what typically AI system might do today: identify key concepts, list the legal cases mentioned, and summarize the outcomes. While that is useful, but it lacks of why. The legal reasoning behind the outcome, it doesn't show how these concepts are connected or how this apply to some similar cases. On the right, you can see the same analysis, but through the lens of the COT. The model doesn't just list the fact, it works through 5 logical steps. The first is like to citing some legal precedent. The second is to explaining how it applies to termination. The third one is defining the boundary of the proof. The fourth is compare the other use cases. The fifth one is applying the logic to a new scenario. This is the reasoning. Then AI is now act as a junior legal assistant. It's parsing the logic of the cases and show its implications. What's powerful here is the interpretability. A legal professional can follow each step, verify the logic, and decide how much to rely on this output. Something you can do with a black box summary. This saves hours of some research and improve some consistency and make legal insight more accessible, not just to the lawyer, but also to the client, analytics, and anyone who need to understand the logic behind the decision. So COT doesn't just automate, it's explained, and that's a key differentiator in some high stakes domain like laws. By now, we have seen what multimodal large language model are, and and also when paired with some COT reasoning, these models can even perform some basic visual tasks. They can describe images, answer some questions about what is sure, and identify high-level patterns. But there is some key limitation for that. While multimodal large language model can observe, they are not optimized for processing. If we ask a multimodal large language model to count people in an image or locate the specific objective, the result often approximate or unreliable. So they lack of some spatial resolution and some accuracy needed for some tasks like bounding box detection, object tracking, or frame-by-frame analysis. That's why we will still rely on some dedicated computer vision model, especially for some objective detection framework like UDO. These models are purpose-built to identify and localize objects in image with some high precision. They can tell us what's there, where it is, and how confident the model is in that detection. But on its own, object detection, stop, and recognition, they can explain why something matters or reason about the next steps. So we bring them two together. For the object detection, they give us some accurate perspective, and for the multimodal large language model, bring some interpretability and some reasoning. And after combining them, they enable decision making from some perspective. So this integration is exactly what powers the system in our demo. And let's now walk through some object detection and how it works. Object detection models are designed to do two things at once. First, is to identify what objects are present in an image. And the secondly is to localize them, usually using some bounding box. These models are the eyes of the system. They translate raw image into some structured data that downstream component, like language model, can work with. Over time, the field has evolved a lot. We have seen several types of detectors emerge, each optimized for different things. Some model prioritize accuracy using some multi-stage pipeline to refine precision, and some other focus on speed using some single-shot architecture to enable real-time performance. And we will see in the next couple of slides, choosing the right model depending on the use cases. If you are running interface on the cloud with plenty of time, you might choose differently than if you deploy on the edge in the real time. In our use cases, for the pole inspection, we need a balance. We want to something that fast enough to be used in the field, but it also need accurate enough to trust. So let's start by looking how these models compare and in terms of the accuracy. Here is comparison of how different object detection models perform in terms of the accuracy. It's measured by mean average precision, and it's also called MAP. The data comes from some systematic review paper and comparing some pre-trained model under the TensorFlow framework and using the standard dataset Pascal VLC. And you can see models like SFD 512 and YOLO 544 lead to some pack with MAP score around 17.4%, while some old models like FastRCNN or YOLO 288 set a little bit slow, around 16 to 17% range. So the key takeaway here is that the new single short detector like YOLO and some SSD configurators are approaching or exceeding the accuracy of some traditional two-stage models while still being faster, and which we will explore on the next slide about the speed of this model. Now that we have talked about the accuracy before, so here is the speed about different models. Specifically, it's like to how many frames per second each object detection model can process. For many real-world applications, like drone footage, live inspection, or some autonomous system, it's not enough to be accurate. The model also need to be fast. This chart shows the FPS benchmark of the same study we cite before, and you can see models like RFCN deliver some strong accuracy before, but at a significant cost of the speed. In some cases, it has low as 6 frames per second. SSD model offers a much more better balance. High performance, vision push close to 16 FPS, making them suitable for some near real-time applications. But the clear leader in the term of speed is YOLO, especially at the higher configurations, which read up to 91 FPS. That's really well beyond what's needed for most real-time scenarios, and it opens the door for deployment on some edge device or some embedding systems. So when we are consider both accuracy and speed together, YOLO model emerge and one of the most well-balanced solution for the practical deployment. Let's now take a close look at the model we have chosen for our object detection pipeline, YOLO. YOLO is a single short object detector that processes the entire images on one pass, making it incredibly fast without reducing too much accuracy. What you see here is the roadmap of the YOLO model familiar, and starting back in 2015 with YOLO version 1. Since then, we have seen some major advancement. YOLO version 3, YOLO version 4 brought some big gains in some accuracy, and the YOLO 5, YOLO 6 improved some performance and usability. And for some recent version like YOLO version 8, YOLO 9, push the limit of the speed, modularity, and the edge deployment alongside the main branch. There are also some several important forks like YOLO X, like PP YOLO, and some YOLO R, each tuned for some specific task and performance needed. The conclusion is near. So YOLO is no longer experimental. It's a powerful production-ready framework with some widespread adoption across a variety of domains. In our case, it gives us some real-time, high precision object detection. We need to kick off the precision pipeline in our system. That said, we will stop here in terms of some deep diving into the object detection, since the main focus of this course is on large language models and the reasoning. So, but if you are still curious about some YOLO internals and some training and optimization strategy, we are happy to dive deeper with you after the session, and feel free to reach out about YOLO later. So far, we have introduced the two core capability of our system needed. One is some object detection to perceive what is happened. And we have the multimodal large language models to reason, interpret, and explain. But in the real world, this component doesn't live in isolation. So we don't just want to a model that see or a model that think. We want a system that can do both, or some coordinate this ability to solve a task. So the answer is through some AI agent. An AI agent is more than just a model. It's some goal-oriented system that can reason, act, observe, and adopt. Often using a combination of the tools and models to solve complex tasks. What you will see here is a simplified architecture of an agentic loop. It starts with a user input, which is passed to a language model, like a multimodal large model. That model decided what we will do next, and it can go on various tools, depends on the task. For example, these tools, it might search an API, it can perform some calculations, it can fetch weather or web data, or it can go on some vision system, like to go on the YOLO object detector. After each action, the agent reflects. It enters some observation phase and evaluations. For example, did I reach a useful output, or do I need any other steps? If it is not done, the loop will be back and take another actions and tries again, just like the human assistant would. Eventually, it produce a structured output, whether it is report, a decision, or a multimodal response. What makes this powerful is that agent can chain capability together. One agent doesn't have to do everything. It can delegate, coordinate, and build on some intermediate result. Let's say you ask an AI, what will be the weather? What the weather will be like in Dublin this Friday? And should I bring the umbrella? A simple chatbot might just guess or give you some canned reply. But for an AI agent, works is really different. It has a goal to give your information accurate answer, and it has the ability to take actions to get there. So here is what it does. Maybe first, it interrupt your request using the large language model. Then it shows a tool. In the case, it's like the weather API, and you send the query to this weather to the API of the website, like the Dublin this Friday. After that, it receives the weather data, read it, and reasoning through it. It's like there are 18% chance of the rain, high wind, or probability smart to bring umbrella, and it returns that as a structured human-friendly answer. The key is that the agent isn't just answering passively, it's actively thinking, choosing actions, and evaluating the result before giving you a response. That's what makes it different from some basic models or chatbot. An AI agent is goal-driving and tool-using, capable for some working through some task autonomously. Now, we have seen what AI agents look like at the system level. Let's break it down how they actually work. What separates agent from some simple model is that they are capturing for some autonomous iterative reasoning, and they often combine some multiple capability of complex tasks. Here are four functions that show up again and again in some agentic systems. The first maybe do some planning. It's rather than just answering one prompt. It's an agent can build an exclusive multi-step plan. For instance, if you ask to write a report, it could first make the outline and then research each point. After that, draft a section and finally reverse and format the output. The second thing is to use. An agent doesn't rely solely on the internal knowledge. They can call on some external tools, like for example, web search calculator and image interpreter, or even some code exclusion environment to gather a new information or take some action in the world. Then is about reflection. After take some action, the agent doesn't just move on. It pause and evaluate. Did that work? Is this the best answer? For example, after writing a summary, the model might recheck the prompt and improve the tone or some completeness or before the submitting. Last is like multimodal collaboration. Perhaps it's the most exciting things here. Agent can work in the teams. One agent might specialize in the vision, and another one maybe in the legal reasoning, another one in some summarization, and they can discuss, critique, and delegate, just like human collaborators. And together, they often outperform a single model. These capabilities are what allow agentic system to go beyond just answering questions. They can do some act, they can adapt and self-improve. This picture shows how multimodal AI system can work together to complete some complex tasks. At the top, we have some traditional software development process. Maybe the waterfall model, it goes step by step. First, design, then coding, and then testing, and finally writing document. Each step is handled by different human roles, like for example, CEO, CTO, designer, programmer, and so on. Below that is agent-based vision, where each role is replaced by AI agent. This agent interact in some structured chat-based pipeline. They pass the message just and the result between each other, just like some human teammate. Let me give you a simple example here. Imagine we want to build a weather reminder app using only AI agent. First, the CEO agent will receive some task, build an app that send weather reminder before I leave home. It break the task into some smaller steps and send them to the other agent. Then the CPU agent design the user experience. So maybe things like allow user to set their location and maybe schedule alerts. The CPU agent choose the technical stacks, maybe using Python to do this or Flask to do this, and with some weather API. And for the programmer agent, will write the actual code and calling the API that CTO recommend, building the front end and make sure some notification works. And the tester agent maybe will check it. For example, what happened if the user forget to enter the location? The reviewer agent check the code for bugs or some improvement. And finally, the documentation agent write a user guide and some technician document. So instead of a single large model doing everything, we have a group of agents, each doing their specific jobs, and they collaborate, pass result back and front, and then improve the final output together. This is what we mean by multi-agent collaboration. It's modular, efficient, and much more flexible than trying to make one model do it all. Let's now walk through the architecture behind our demo. A real example of the multi-agent AI in action. This system is designed to automatically analyze some utility pole images and generate some details inspection report, combining some computer visions, some language understanding, and the reflection. We have built it using some team of lightweight task-focused agent. The first is file agent. This is the entry point. It takes care of some uploading images and preparing them for some analysis. The model agent, it's load our object detection model, YOLO. It gives us some fast and accurate identification of some visible defects. Perception agent runs the detection on the each image, location some issues like some rust, cracked, or some performance, and return some bounding box with a confidence score. And for data processing agent, will take the raw detection result and turn them into the cleaning summary, things like what was found, where, and how confident the model is. Report agent is where the language model comes in. It's using a multimodal language model to generate a structured readable report based on some detection summary before we have generated by other agent. And then finally is some reflective agent. It's you add one or more layer of some intelligence. It reviews the report, agent generated report, and ask, is that accurate or is that anything missing? And then update the output with some improvement maybe using some COT style reasoning. Yeah, and also we will have one more agent is like control agent. This agent is coordinate the entire process. It manages the flow of information, hands tasks, and to the right agent. And it ensures the final report is complete and high quality. So together, this forms a fully automated agentic system whether each part will handle a specific role. And the result is robust, scalable solution for some utility pole inspection. Yeah. Then we will come to the demo part. I will share the I will share the link of the demo in the chat. Moment. Oh yeah, thanks Yilin for sharing that. Yeah, we can get into the demo here. Hopefully everyone, I will give you 1 minute to open the Colab notebook in our chat. Yeah. Hopefully everyone will open it now. Yeah. For this lab, we are going to build and walk through a simple multi-agentic AI system for some automated object detection, similar to what we will show earlier in the slide. Specifically, this lab will show you how to build a multi-agent workflow using Python and also using YOLO for some visual perception and also to detect some damage on utility poles. And it can also simulate some different AI agents that can handle the task, like the file input, for example, some model loading, and also object detection and the report generation. You will see how each part of the system works step by step and how agents communicate with each other to complete the whole pipeline. Before we begin, let's make sure we need to have some environment set up here. Yeah, so in this step, we will install all the required libraries. And like for Archalytics is for getting the YOLO model. Matplotlib is for some visual analysis. Grok is the place we need to get the multimodal large language model API. And
sorry to interrupt. Could you please check if you have the permission, have open the access to everyone to
the code?
see it? Yeah, the code.
Okay, please give me a sec.
Because some people say.
I think it is anyone with the link.
Okay. Yeah, I think that works. Yeah, please continue. Thank you.
Or maybe I can paste the yes to.
Yeah, I think that works. That's okay.
Okay, yeah, thank you. Or maybe I can send this to your guys so you can check it. Okay, and for the JDAN, yeah, and this is the file we can, download the folder I have prepared before to one. There is one prepared fine-tune YOLO model and also some test images for the Google Drive from the Google Drive, and I already uploaded it, and which we can use it and see the input later in this lab. Maybe let's run it at first. Here it will take a little bit of time to run the environment setup. It maybe take 2 or 3 minutes. And for now, we can do something like, because we need to acquire some multimodal large language model. So here we need to have some, you have some API to get the API key for the some multimodal large language model. So we can, before it is executive, we can go to the Google, search the Grok, and to get the API key here. Yeah, maybe and so far, if you are first to access this part, you may need to do some registration, and after that, you just click create the API key here, and in here, you can enter some name of your API key. Anything could be used. Like for example, we can use test as the name of the API, and submit it. And here we will get the API key here, and it is free to use, and no more cost for us to have some API call. But here, be aware to copy it now because it won't be display it again. So we can copy it and done. Maybe we can save it in somewhere safety. And later we can using this API to do some work we'll show it. And after that, before it is still setting up the environment, we can see some coding here. The JSON is this is to get the pre-trained model, and this to get the images. And this is to have some to unzip the image files. And after it is finished, this part is finished, we can open up the files here. We can see we have the user model in our environment, and also we have some images here, and we can open it to see with some images for some posts, some damage on the post. Yeah, it's finished, and after that, we can start by to do some importing the libraries, and we will be using for this lab. The first OS and Shuttle is some standard Python library. It's for working with the files and folders. We will use this to move the images and manage directions during the pipeline. And the base 6.4 is used to encoding images, so they can be passed into the language model in a format it understands. And for matplotlib and NumPy, if you are familiar with Python to do some data analysis, you will be really familiar with it. It's to help with image visualization and also do some numerical operations. And I have talked about this before. It's to get the YOLO model. And for the Google Colab, the file is allowed us to upload file if we want to run the notebook in the Google Colab. For example, like we can upload some other images into the environment. And the last is Grok. Make sure we already have the key of the Grok. And after that, we will need to insert it to get some multimodal large language models. And also we can see, after we have the key here, we can click the documentation. We can see there are some feature of the models here available. And this is only for the text model. And here is some speech to text, text to speech, and also reasoning model and vision model. Because we will do some object detection. So today we want to use this model, Llama 3.2 19B vision. We can have the model ID also, but it's already in our code. Okay, let's kick off about the agent, the first agent in our system. Okay, the first one is this agent is a file agent. This agent is responsible for handling some image input. The kind of the data that you know to field technician or some inspector sector would collect. In this lab, instead of using web interface, we simulate that by printing the agent to a folder of some sample images that we have downloaded earlier. Is these images, the images in here. And And here is what this agent does. Okay, it scans some dictionaries and looking for some valid image files. It's like to scan this folder and find if these files are a PNG, JPG, or JPEG format. And once it finds this, it copies them into some working folder. And where this working folder, some detection agent will access them later. The detection agent is model agent. Yeah. And it also keep track of how many images were found and optional to print them out so we know what comes next. This simulates a real-world process, whether inspectors upload images from the field and the system begin analyzing them automatically. Once the images are prepared, they are ready to process the next stage, and which is a model agent. It will be run the YOLO for some object detection. You can run this. For the model agent, this agent is responsible for loading and preparing the object detection model. In our case, we are using the YOLO model. It support two options. The first, you can load the, like here we can see, you can load the pre-trained model work, and it can it already works well on some general objective categories, but it's not really well for our target because using this model, it will have some difficulty to identify some damage here. Yeah. Because it's for general model, and for us, we will using what we uploaded. Here is the best.py. It's we have fine tuning the YOLO model and make it more suitable for our tasks. And so once our model is loaded, it will pass the model into the perception agent. It will run some detection process for each input images. And at this point, the model is ready to receive some images, run the interface, and return some bounding box and class labels and some confidence scores, all of which will be used in the next stage of the pipeline. And so for the model agent is to set up the brain of some visual part of the system, the object detector, and make it available for some downstream agent to use. Now the model is loaded by the model agent. The actual object detection is handled by the perception agent. This agent takes the loaded YOLO model and apply to each image passed into front of the file agent. They have gives us some images to here, and here is what it does step by step. At first, it will receive the image from the file agent, and it will using YOLO model to run this interface to detect the damage on this image. And the result include the bounding box, class labels, and some confidence scores for each detect object. So in our case, we are detecting things like rust steel, which are labeled in the customer model. Yeah. After detection, the perception agent can also visualize the result by drawing some bounding box over the detect area, maybe using OpenCV library, and these annotated images will be saved to display in this notebook. And More importantly, the agent also pass some structure detect data, include some object type, coordinate, and the confidence to the next agent in the pipeline. That the next agent will interpret the detections and explain what they mean using some models, language model to do some processing or before that. So at this point, we have completed some visual perception stage of the system. We have taken raw input images and extract some meaningful detection result. So yeah, next step is to have the data processing agent. This agent is before we use something sent to the large language model, we need to format the detection result in a way that makes sense to the next agent. So when using data processing agent to receive the raw output from the user, include some object class name like a bounding box coordinate and some confidence scores, and turn it into a structure format. In some cases, it may also filter out some no confidence result, group similarly object together, or summarize how many instances of each object were found. Once the data is cleaned and organized, it will pass to the reasoning agent, which will generate the inspection report. And in our system, this will formatting step is the formatting step is really crucial because multi-modal large language model don't work well with some raw detect data. They need some clear input with some relevant context. This agent help make that bridge between some perception and reasoning. Now that the data is pre-processed, let's move on to the next step, is using large language model to interpret the image and generate the report. Yeah, now we are at the most important step of this system is the reasoning agent. This agent takes some structure detection result and use a multimodal large language model like we shown before. It's using Llama 3.2 19 billion vision preview here. And it's using this model to generate a full inspection report. And I will show you how it works. First, the agent construct some detailed prompt like I have shown here. It's like some COT prompt. Here, I already set it ready for you. And after that, it introduce some detection summary, some like what objective were found, where they were located, and how confident the model was. It asks the model to analyze the images and damages data across some seven specific categories. Like here we have shown like material identification, defect analyze, environmental impact, structure integrity, safety components, maintenance recommendations, and also conclusions. The model responds with a structured, human-readable report covering all aspects of the post condition in clear technical language. But the agent doesn't stop here. It will have some reflection here. It's also using reflection prompt to do more jobs. After we have the first version of the using this model to generate the report for our system, we will have the sixth step, reflection. It will ask the model to critically review the output and evaluation if this the first draft of the report, if there are all seven, let me see. check it. Like it's like does the report clearly cover all 7 inspection area like we have shown here? And also, is it technically correct, logically consistent, and free of batch statement? Yeah. And if some also there needs some improvement, the model will rewrite it and rewrites the report. And if not, the model will return the final version. And this is exact the reflection step make the output more reliable and polished. And it's a great example of how agent reasoning adds structures, quality controls, and transparency to AI-generated result. So after that, we will get the fully inspection report ready for human review and direct integration with workflow. And this report agent is nearly the last step of agent. It helps to present the final output to the user. Like using this model, we have the report, and before we have the picture of the YOLO detection. Using YOLO to do object detection, we using report agent to combine these two together. So our report will have the picture and also have the report. So how it is works, like first it takes the output from the YOLO model and displays the annotated images and completely with some bounding box showing the detected object and some area of the damage. Then it prints out the inspection report generated by some reasoning agent. And this one that were, through the both reasoning and reflection. So, yeah. And the final report will be like the final result of the entire system will be like that. At the beginning, it will be have the visual output that clearly show what was found in these images and have some detailed structure report that explain why this funding. What this funding meaning, how serious they are, and what should be done next. This kind of output is easy to human to read and act on. Whether you are a technician in the field or an analyst review inspection remotely. So with this agent, the pipeline is completed from image input through perspection, reasoning, action, and all had by some series of lightweight and module agent work together. Now, we will arrive at the final part of our demo, where all the agents are connected together by the control agent. This agent is coordinate the entire pipeline from image input and all the way to the final report. But in this version, we have added something, and it's like have a simulated feedback loop between the reasoning agent and some action agent, report agent. And the report will be passed to action agent, which will show the images. After that, instead of ending here, we simulate user feedback by asking reasoning agent to review its own report and make some improvement. The loop will happen twice, which simulate 2 rounds of the reflection, just like some human inspector improving a draft. This creates a more dynamic, more intelligent interaction pattern where the system can evaluate its own output and refine it before final delivery. Even though this is a simple demo, but the structure opens the door to some real-time human feedback and some multiple collaboration agent, or even to do some thing more. Yeah. So That was the real power of the AI agent AI. It's not just automation, it's interaction and it's iteration coordinated by a control layer that keep everything module and composable. And we can run this demo now. We have run the first S2 file. This is a module agent to choose the UDO model. This is a perception agent to do the detection. Data processing agent to do some data processing, and the reasoning agent to give some textual report, and the report agent to combine the visual and textual report together. And we have the agent coordinators to design the pipeline for the whole agent. And here is we can run it. And before that, we have the Grok API key. We need to paste the API key here. We can run it and see the result. Here, we need to enter the floater path containing the whole images. As we before we have the images, we have already downloaded images. We can click the file here, and this is the image file, and this is a folder containing some post images, and we need to right click it and copy the path of this image folder. Because our file agent only to deal with the folder, so it will deal with all the images inside. So we just need the folders path, not the pictures inside. And we can enter it. So we can see what will happen. And at the beginning, model agent load the model. Oh, sorry. And some agent to detect object, and here is the figure of the detection, and here is the report of this report. There are some things here, and everything showing here. And after doing the first times, we need to have the 2-round feedback. So we have the feedback for this report, and like someone review it and modify it. Like here is the first draft of the model, and then we have the second draft. It's improved by the for the first one. We can see the UDO model can detect everything really clear here. But we also can using some pre-trained model to do some general detection tasks. But maybe we can test like using this code. Have the Grok API key here. Right, see if using the UDO, just UDO model, what will happen? We can also have the path here. And we can see it cannot detect any damage on this figure. But using our fine-tuned best PT model, it will be, it can use for detect something here. Okay. That's all thing we will discuss today, and let's come to the quiz time.